we're talking about logarithmic functions. So the previous section we had talked about exponential functions, which were y equals a to the x, where the variable was in the exponent, which makes it an exponential function. Now we want to talk about the inverse, something that does the opposite. So the convention is going to be that the base is b. So we were really going to say y equals b to the x. So the inverse of that is what we're going to call the log. Right? So when we say y equals log base b of x, we're going to mean that b to the y is equal to x. And this is something we're going to be talking about over and over and over again. So b to the y power equals x. b to the y equals x. That's the answer to number one. And so in words, I cannot stress this hard enough, that the log is the power or the exponent. The log is the power. I'm probably going to say that 15 to 20 times in the next 15 minutes or so. The answer is b to the y equals x. When I write f of x equals log base b of x, this is the logarithmic function with base b. For number three, it says log base b of b. And the question is, what is that? And so, if I don't know what it is, I call it x. And so the question is, what is this? Well, again, the log is the power. So the question is, what power would I raise b to in order to get b? And that number is 1. First is equal to b, and therefore the power is the log, and therefore the answer is 1. And so if I had log base 3 of 3, that is 1. Log base 7 of 7, that is 1, because 1, 7 to the first is equal to 7. And log base 3 of 3 is 1 because 3 to the first power is equal to 3. For number 4, log base b of b is the number 1 because b to the 1 is equal to b. I ask, well, what's log base b of b to the x? We could say this in a number of ways. First of all, I had mentioned that log base b and b to the x are inverses, so these should just cancel, and you're left with x. But another way to think about it is that what power do I raise b to in order to get b to the x? And that power is x, right? b to the x power is b to the x. So the quick and dirty way to think about this is that the log base b and b to the x, they cancel each other out, and you're just left with x. So they just cancel, and you're left with x. The answer is x. For the same reasoning, b to the log base b of x, they also cancel each other out. Cancel each other out, you're just left with x. And you'll see this as we go up, but so this means that 3 to the log base 3 of x is x. 7 to the log base 7 of x is x. They just cancel each other out. And up here, log base 11 11 to the x is just x. So that, again, the exponential and the log base b of x, they're inverses, and so they cancel each other out. You put one inside of the other. Now, from what we had said from the last section, we said that the domain of the exponential function was negative infinity to infinity, and the range was 0 to infinity. And so because the log is the inverse, then that switches. So the domain of the log is 0 to infinity, and the range is minus infinity to infinity. There's some special log functions. If I have log and the base is 10, then we just write log of x. So if you don't see the base written, then the base is assumed to be 10. And that is called the common log. And you write it as log of x without any base. Last time we defined e, and so if you have log base e of x, we just write that as ln x, and we call that the natural logarithm. And if you get the calculus, you'll know why we call it the natural logarithm. But that base is particularly nice, and this is a base that's in the calculator. Okay, so exponential form, I'm going to go back and use the definition. Earlier we said that if log base b of x is equal to y, what did that mean? That meant that b to the y power is equal to x. Right? So that meant, by definition, that b to the y power is equal to x. And so this form here is called logarithmic form. So again, these two statements are saying exactly the same thing. But this form is written in terms of a log, and this form is written in terms of the exponent. So this is called exponential form on this side. This is exponential form, and this is logarithmic form. Here, this equation is written logarithmic form because there's a log. And so to write an exponential form, you take the base, which is 5, you say 5 to the 4th power is equal to 625, and you literally put that in that way. So 5 to the 4th equals 625. That is the exponential form of this logarithmic form. So we'll be performing this procedure for the next few problems. 4 to the 8th power is equal to m. 4 to the 8th power equals m. That is exactly the answer. Do not simplify. b to the 4th 16. So again, you just take the base, raise it to the exponent because the log is the exponent. It needs to be 16. And that's the answer. You put it in just like that. And here, conveniently, they already give you the equal sign. So b to the 4th equals 16. Don't solve. Just write it as it's written. here we're going backwards again. So if we have y equals log base b of x, that means that b to the y power is equal to x. And so now we're starting over here in exponential form, and we need to write it in logarithmic form. And so writing it in logarithmic form means filling in a few blanks. And so there's a blank here equals log base blank of blank. Right? And so here, the things to remember is that the log is the exponent, and therefore this thing here always has to be the exponent of the exponential equation. So in this case, when you look at this exponential function, 4 is the exponent. And so 4 would go over here. This number down here is always the base, and the base is the number that always has a power on it. And therefore, because this is 3 to the 4th, it's the 3 that is having a power on it. And so 3 goes here. Process of elimination, the 81 goes there. So you can always just say this is the result on the other side of the equal sign. So that's the result. The answer is 4 equals log base 3 of 81. That is the logarithmic form of this exponential equation. And we'll do that for the next few problems. Here, log base blank of blank equals blank. Again, the exponent goes here, -4. Exponent. The base is 3, and 1 over 81 is the result. Answer, log base 3 of 1 over 81 equals -4. That's the logarithmic form of that exponential equation. Here, I'm trying to intimidate you, but I can't, right? So the remark here is that when I write the third root of a number, I mean x to the 1/3 power. And so really I'm saying that this is 8 to the 1/3 equals 2. And when we write it this way, then it's easy to fill in these blanks. The exponent goes here, it's 1/3. The base is 8, and 2 goes here, and that's the answer. And by the way, you can always check because it's supposed to be 8 to the 1/3 equals 2. And that's exactly what that's saying. Here, log base blank of blank equals blank. The exponent here is 6. The base is y, and the result goes there. As you see it. And when you're putting in the log, you'll need the subscripts. Log subscript y of 301 equals 6. We want to know this number, log base 2 of 4. So what is that number? Well, this is, the log is the exponent, right? So this, whatever this ugly thing is, this is the number that you raise, this is the exponent that you raise 2 to in order to get 4. So what number do you raise 2 to in order to get 4? And that number is 2, right? So this is 2 because 2 to the second is 4. This number is 2 because 2 squared is 4. This one is tough because it's asking what power of 2 gives you 512. So let's get 2 out. So 2 times 2 is 4 times 2, 8 times 2, 16. That's 4 times 2, 32, 5 times 2, 64 times 2, 128. So that's 7 times 2, that's 256. And then times 2 is 512. I think that's 9. So we can check that 2 to the 9th is 512. And therefore, log base 2 of 512 is 9 because it's the power. You need to raise 2 to in order to get 512. So we see that that's the game. We're just looking for the power. There's some things we have to remember about certain special powers, that negative exponents move things to the denominator. So for instance, x to the negative 1 is 1 over x. So that if I see 1 over 9, that's really 9 to the negative 1 power. So when we see log base 9 of 1 over 9, we're really saying log base 9 of 9 to the negative 1. And then you ask, well, what power of 9 is 9 to the negative 1? And that is negative 1, because 9 to the negative 1 power is 9 to the negative 1. So it's just asking what power that is. The answer is negative 1. This one's a little funkier. So now, how do you get 243? Well, going back, how many 3's give you 243? So it's 3 times 3 times 3. That's 3 of them times another 3. That's 4 times another 3. That's 5. So I know that 3 to the 5th is 243, but this is 1 over 243. And so from our comments before, it's flipped, then that means that the exponent is just negative. So it's negative 5. And then the final remark, or the semi-final remark of that's needed for exponents, we kind of referenced earlier. So we said earlier that the third root of x is x to the 1/3. Well, for that same reason, for similar reasons, I should say, the square root of x, there's an invisible 2 here. This is x to the 1/2. And so if I'm asking what power of 3 is the square root of 3, well, the square root of 3 is actually 3 to the 1/2 power. And so the power of 3 that the square root represents is 1/2, because again, log is just the exponent. 22 brings everything, the last 3 or 4 problems, all together in one problem. So now when I ask, well, what power of 2 is 1 over the square root of 2? Well, we say, well, first of all, there is a square root, and so that is 1 over 2, and the power is 1/2 from the previous problem we just discussed. But then this is in the denominator, and so now the power of 1/2 is really negative. So when we ask, well, what power of 2 is 1 over the square root of 2, we say, well, there's certainly a 1/2 because of the square root, and because you're in the denominator, that power has to be negative. So the answer is negative 1/2. Couple things going on here. Log of 1 over 100. The first thing is that we notice there is no base, and so I want to reference something earlier that I said about the common log, that again, if you see no base, then that means that the base is 10. So no base. If you see no base, then it's assumed that it's base 10. So then now the question becomes, well, what power of 10 is 1 over 100? Well, we know that 100 is 10 squared. We also know that because you're in the denominator, that this is really, I can write this as 10 to the negative 2 because powers in the denominator are really negative powers. So when I ask, well, what power of 10 is 1 over 100, it looks like the power is negative 2 because 10 to the negative 2 is 10 to the negative 2. The answer is negative 2. So notice what we're doing. We're trying to make the number inside the power of the base in question. These are these 24 and 25 are testing this idea that, again, if I write log without an obvious base, then the base is assumed to be 10. So this is really log base 10 of 10 to the 11th. And as we said earlier, that if you have log base b of b to the x, then you just flat out get x. They cancel completely. And so the log base 10 of 10 to the 11th is just flat out 11. They cancel. Here you're just reversing the order. So if I have log 10 to the log base 10 of 26, they flat out cancel and you're left with 26. We're using the other convention as well, that when I write the natural log of x, then that is log base e of x. And so when I write the natural log of e to the 6th, I'm really saying log base e of e to the 6th. And that looks bad, but again, this directly references this. That no matter what the base is, no matter how bad it looks, right? That log base b of b to the x is x. In this case, the base is e. So log base e of e to the 6th, again, the same canceling occurs because they're inverses and cancel each other out. The answer is 6. This is just reversing that order. So e to the natural log of 135 is equal to e to the log base e of 135. They cancel still, and it's 135. So no matter whether you're putting the log inside of the exponential or the exponential inside of the log, this type of canceling still occurs. Here, we're just talking about using these log rules in conjunction. So log base 2 of log base 8 of 8, you just start inside. And you notice that log base 8 of 8, we said this earlier, that the power of 8, that 8 is 1. Right? 8 to the first is 8. And therefore, this number is 1. And so this is equal to log base 2 of 1. Now, we have yet to say this, but the power you need to raise 2 to in order to get 1 is 0. And so, because 2 to the 0 is 1, because any number to the 0 power is 1. Right? And now, while I'm here, there is nothing special about 2. And in general, log base b of 1 is always 0 for any base. So drilling on that pretty quickly, log base 7 of 1 is 0, log base 2 of 1 is 0, log base 11 of 1 is 0, and so forth. The answer here is 0. Log base 2 of 2 is 1, and again, log base b of b, if these two are equal, is always 1, because 2, in this case, 2 to the first is equal to 2. And the log is just the exponent. Log base 8 of 1, we had mentioned this rule earlier, that I need the power to raise 8 to in order to get 1. That power is 0. Right? So 8 to the 0 is 1. And so from what we said earlier, log base b of 1 is 0 for any base because it's the power you need to raise b to in order to get 1. Here's some more canceling. Again, log base b of b to the x is just x, and therefore log base 2 of 2 to the 7th, I need the power to raise 2 to get 2 to the 7th. That power is 7. 2 to the 7th is 2 to the 7th. I think that is it. So, I believe these are the answers now. Yeah. So that is it, and I hope it helps.